Welcome back, everyone. We're looking at Chapter 15 today. Chapter 15 is a little bit longer than previous chapters. I think it's longer in the literal sense of it might be a few more pages than other chapters we've looked at, generally pretty short. And this chapter is really packed with a bunch of important stuff. So I think what I'm going to try to do is break this chapter down a little bit and try to go a little slower here. I know that makes a little bit more watching, a little bit more stuff to do in this week, but I'm hoping that it pays dividends in that I really don't want to skip any details in this section if I can help it. And so what we're going to be talking about is the idea of a quotient group. And what that means in practice is that it is a way of identifying a chunk of a group, a specific normal subgroup will be the technical term, and essentially setting it equal to the neutral element or zero if you like. And this process, which feels like it might be something that you might, why do you want to do that? What's the point of that? Will turn out to be incredibly helpful for enriching our understanding of homomorphisms and homomorphic images of groups, as well as giving us ways to systematically break groups down into smaller and smaller pieces. And so this tool turns out to actually be close to indispensable. But in order to set it up, we have to kind of go through the process. And so towards that end, we're going to start with the first theorem of this chapter. And the theorem says, so we'll call this theorem number 1, which says if G is a group and H is a normal subgroup, that's not how you spell subgroup, of G, then AH equals HA for any A. And it's funny because when I saw this, I was immediately confused because for me, this is actually how I grew up, so to speak, the definition of normal subgroup that I know. So I have to remember that for Pinter, being a normal subgroup means you are closed with respect to conjugation. And so, okay, now I know what we have to prove. So let's say that we have some, I don't know, let's call it X in A times H. Then in particular, this implies that X is equal to AH, little h, for some little h in big H. And because this big H is closed with respect to conjugation, we also know that AHA inverse belongs to the subgroup H. But now the magic is that X is equal to AHA inverse A, which I will group up as AHA inverse times A. And so what we see is, since this thing is conjugation closed, this thing lives in H, and this A has now managed to migrate over to the right. So just to sort of summarize, we had AH on the left, now we have HA on the right. So we have X in HA. And so what you see here is that I could run this argument in either direction, either by inserting the A inverse A on the right, or I guess it should go the other way if I wanted to do the trick the other way around, and A inverse on the left, and prove the reverse implication. And so therefore, we have proven that AH is a subset of HA, and by analogous reasoning, HA is a subset of AH, and so together, these are equal. Okay, cool and good. We're going to need this property going forward for our next theorem. Before we do the next theorem, a little bit of discussion. When we have these cosets in general are just sets. They don't really have any nice properties or features that are exploitable for a general purpose. However, when you have a normal subgroup, normal subgroups can give them extra properties. So I'll say they endow cosets with extra structure. And I'm going to elaborate on what I mean by that now. So suppose, just for the sake of moment, that we don't know what kind of subgroup we're dealing with. And we might want to ask ourselves, okay, these things live in a group. So to what extent can we work with them as if they're in a group? In other words, to what extent do they inherit a multiplication operation from G? So if I wanted to do this, we could try to define multiplication. And it seems to me that the natural way to do that is to say, if I have a coset HA and a coset HB, the reasonable way to define this, I'll put a question mark since it's not currently clear, would be to write this as H and then times the coset of AB. And this seems simple and straightforward, but the issue is it's not clear that this is what we call well-defined. And so we remember that well-definedness, or just to say that something is well-defined, means that it does not depend on any choices such as a representative of a coset. So what I mean by that is HA being a set will be equal, for example, to lots of HCs, and we can also have HB being equal to lots of HDs. And according to these multiplications, if I try to multiply these, the formula that I have is that this should be equal to HAB. These should be equal to HCD. But it could happen that these are different. And so that would be a problem for our notion of multiplication. Let's take a moment and observe that this can, in fact, happen. Pinter does this with an example. He says, okay, let's fix a specific example here. How about we take G equal to S3? And then, in particular, he takes a subgroup, H, which consists of the neutral element, and then he uses the letter alpha. All that matters for us is that alpha here is a transposition, but in order to do the calculation, we should probably specify which, how do I say this, which permutation this is. So let's call this permutation 1, 2. And then if we do that, then he takes a look at the rest of the cosets that we can construct. And in particular, we can ask what is H beta and H gamma. And both of these things, I'll let you guys pause the video and check, are equal to the sets of beta and gamma. Whereas H delta and H kappa these guys are the sets of delta and kappa. On the other hand, the problem that we run into is H of beta dot delta is the same as the coset of the identity element, and H gamma dot kappa, this is not. This is, what is this? This is H beta. And in general, these are different. I don't know why I said in general. They're just clearly different. The coset of the identity element is just the subgroup, whereas H beta is the thing I calculated above. And so coset multiplication is not usually going to make a well-defined operation on cosets of a subgroup. It's not going to happen. However, if the group is a normal, sorry, if the subgroup in question is a normal subgroup, then it will work. How long have I been talking for now? 10 minutes already. Okay, I'm going to do this theorem and then we're going to stop here. So this will be theorem 2. And that'll be enough for this video. Coset multiplication is well defined for normal subgroups. H of G. Okay, and the proof of this is not so bad. So let's start by writing out exactly what it means. In particular, what's the best way to write this? HA equals HC, HB equals HD implies HAB equals HCD. I guess this is just, continuing the notation from before. Okay. Now for the proof. So let's start with HA equals HC. In particular, this gives us that A is in HC. And so I can write A equals some little HC. And we're going to have a bunch of little h's running around in this proposition. So we'll number them. We have an H1. The same reasoning with HB and HD tells me that B is in HD, or B is equal to H2 times D. And so now, let's see what we get if we multiply these things. I get AB equals H1C times H2D, which doesn't seem, particularly remarkable at the moment. However, I can isolate CH2 in the center here. And we know that this CH2 lives in, sorry. Oh, no, it's okay. I was a little confused for a second. I was wanting to use this HC, and I was briefly concerned that this is a right coset when I have a left coset here, but that's exactly the thing I'm assuming, right? These are for normal subgroups. And so CH2, the proof goes on just fine. CH2 is a member of CH, but that is the same thing as HC. And now this is kind of the magic, is that because these are the same thing, it must be that CH2 is equal to H3C because it belongs to HC. And now we can finish the regrouping. This is H3CD or H1H3CD. And because H is a subgroup, this is just something in H. And so what that means is I have succeeded in taking the product that I wanted and showing that up to multiplication on the left of something in H, that these are equal to these. And that's what I wanted to show, right? HAB, in this case, I could put the identity element over here if you like, right? E is surely in H, is equal to CD times something in H, something different in H in all probability, but that's fine because these are not group elements of H, they are cosets of H. Okay, I think at this point now, we have said enough for one video. There is quite a bit more to talk about with groups, so if you need a moment, take a moment, go get up, stretch your legs, get a glass of water, whatever. We're going to put a little pause here, and then we'll pick up next time, continuing to investigate this group operation on these cosets because, well, I guess I've spoiled it a little bit. That's going to be the next step, is that coset multiplication will endow the collection of cosets with the structure of a group.